In part 1 of lecture 2, we will discuss bootstrap processes and interrupts. There are many parts to a modern computer system, many of which are represented here. In addition to the CPU, the brain of the computer, there is main memory and various input-output devices, all of which are connected through controllers or interfaces. The CPU and the controllers work concurrently, and since they all access memory, there is a need for a memory controller to synchronize the process by which the CPU and other device controllers access memory. This prevents memory from being corrupted. When the computer is turned on, there isn't anything stored in memory other than the contents of its ROM. The computer's first job is to load the operating system, because without the operating system in memory, there's very little that the computer can do. In the early days of computers, loading the operating system might mean toggling a small program into memory, which then loaded the operating system. These days, small programs that can load the rest of the operating system are usually stored in ROM. Because this allows the computer to get itself started, we call it a bootstrap program, because of the 1960s notion of letting someone pull themselves up by their own bootstraps. The bootstrap process for different computers takes different amounts of time. Booting a PC can take just a couple of minutes, while booting a mini computer can take 20 minutes, and booting a mainframe can take more than an hour. The bootstrap process means initializing registers, device controllers, and memory, as well as loading the operating system. It also means initializing whatever data structures the operating system may use, and starting system processes that the operating system may need to provide services that user programs require. After the operating system is loaded, it then waits for the first event, which may be input from a terminal, a service request from its initial process, or just another tick of the system clock. When that happens, the operating system will take over again and perform whatever work is required of it. For all practical purposes, the operating system is an event handler. When any of the different events that can trigger an interrupt happen, the operating system takes over and provides whatever servicing the system may require. The events usually occur because of something in hardware. A disk operation is finished, a system clock ticks, a user program tries to access a part of memory that is not available to it, and so on. There are also some events that the program causes itself, such as a request for a service of the operating system, or trying something that it should not do, such as dividing by zero. All of these events require some action by the operating system, but the actions that it will need to take will be different depending on the particular event that has occurred. Each of these events cause what we call an interrupt, because it will interrupt whatever else the computer may be doing. The interrupts can occur during any part of the instruction cycle. Asynchronous interrupts are triggered by the computer's hardware because it needs servicing. A disk operation may have finished. The computer's clock may have ticked. A character may have been typed at a terminal. Any of these may have caused the interrupt, and the operating system has to attend to the needs of this device to ensure the efficient operation of the computer system. Other interrupts may be synchronous, occurring at specific times in the instruction cycle. These usually will be due to one of two potential causes. These causes include errors in executing instructions and they are typically called violations or faults. Depending on the computer, they are basically the same thing. Violations can be because a program accessed the wrong part of memory, or because of division by zero. Other causes are requests for system services by user programs. Most computers have special instructions that allow them to ask the operating system for specific services. The Intel processors that are used in PCs have a special instruction int, which allows a user program to call a particular interrupt directly for whatever service the program needs. Ultimately, processing an interrupt requires transferring control to the appropriate interrupt handling procedure. But as any assembly language programmer knows, transferring control to another procedure takes several steps. After the CPU stops working on another task it is doing, it has to save the contents of the registers so that the program running at the time of the interrupt signal can resume later. Then it has to transfer control to a general interrupt handling procedure. This procedure has the job of determining the nature of the interrupt and to which interrupt service routine it must transfer control. After the interrupt service routine does everything required to service the interrupt, it will transfer control back to the application program. The fastest way to transfer control to the appropriate interrupt service routine is by using an interrupt vector. It is an array of addresses that are usually stored at the lowest end of memory. These addresses correspond to the starting addresses of the various interrupt service routines. When an interrupt signal is detected, and the operating system determines which device signaled the interrupt, control can be transferred directly to the interrupt service routine. This is a pretty fast method for transferring control to the appropriate routine, so much so that most computers provide hardware support for this. Most of the work of the operating system involves handling the details of managing the computer and its resources. Turning over the CPU to the operating system provides a good example of this. In addition to saving the register values used by the program being interrupted, the operating system also needs to save the address of the next instruction so the program can continue exactly where it was interrupted when it regains control of the CPU. Most operating systems will disable other interrupts while processing interrupts. While they don't always have to be disabled for the entire time that the interrupt is being serviced, there will be parts of the process where it is essential that the operating system procedure not be interrupted. If it is interrupted during these critical sections, it is possible that the first interrupt may be lost.